the voice. Yeah, no audio.
Okay. I think we will share it again. There's a problem. Huh? What is the problem? I think there is a voice along with the film. Otherwise, we are just trying to reload it. I don't know why.
Chivasu, I can hear you. No problem. Audio is okay to me.
But the film audio.
Film a little bit it was shown in between. Then it was showing properly.
Okay.
I saw it. That fuel bundle palace.
But it seems. Where is it?
It's not audio along with the film is not audible.
But I think along with there is no audio. I think only just.
In the folder. Close it. Folder. Go back to the please open it. Now you open this film, starting with the film here. Share. Share sound.
It is coming. It is
Okay. Now it will.
Coming.
Fuel complex, Hyderabad.
Sorry.
Yeah. Audio also there.
Of atomic
Okay.
energy was conceived with the mandate to fuel the nuclear power program of the Government of India. An ISO-certified organization, NFC is the only facility in the world today to have a comprehensive manufacturing cycle from ore to core, involving the processing of both uranium and zirconium streams under one roof. NFC made a modest beginning in 1971 with a production capacity of 100 metric tons of fuel. Today, it's the world's largest producer of fuel for pressurized heavy water reactors. Zirconium's exceptional nuclear properties make it an important structural material for making nuclear fuel assemblies. Zircon is extracted from the beach sands of Kerala. NFC converts hydrated zirconia into zirconium oxide by the solvent extraction route. It is then converted to reactor-grade zirconium sponge using Kroll's process. The sponge is melted to form ingots which are hot extruded into tube blanks, slabs and bars that form the primary material for a wide range of nuclear components. The extruded blanks are subjected to pilgering, annealing, rolling, swaying, etc. to manufacture fuel tubes and other components. The zircaloy tubes act as a cladding for uranium dioxide fuel pellets. Uranium dioxide fuel is extracted through ammonium diuranate route, which is further processed into pellets using powder metallurgy techniques. These pellets are loaded into zircaloy tubes to form a fuel element. These elements are then integrated to make 19-element or 37-element fuel assemblies. Similarly, NFC manufactures other complex fuel assemblies and in-core structurals for boiling water reactors and prototype fast breeder reactors. Reactor fuel thus produced follows stringent process controls to ensure world-class quality. These best-in-class processes are a testimony to NFC's innovative spirit and expertise in making India self-reliant in nuclear power. The production of zirconium sponge got a vital boost in the year 2009 with the setting up of the zirconium complex at Pariyakayal, Tamil Nadu. To cater to the upcoming nuclear reactors, NFC is setting up one more unit at Kota, Rajasthan, with a capital outlay of rupees 2,401 crores. The product matrix of NFC is wide and covers the entire gamut of requirements for nuclear reactors, high purity materials, and special seamless tubes catering to nuclear and non-nuclear sectors like defense, space, fertilizers, etc. NFC is an acknowledged leader in manufacturing extremely long-length thin-wall seamless tubes, as well as U-bend tubes conforming to strict dimensional control. NFC has developed state-of-the-art facilities and innovative process technologies to manufacture tubes of various grades of stainless steel. NFC has developed R grade niobium sheets for the accelerator program at RRCAT, Indore, a collaboration with Fermi Lab. NFC has also developed high purity materials of 99.999% purity for use in highly specialized applications. To NFC goes the credit of developing the world's first niobium, 1% zirconium and 0.1% carbon alloy for high temperature applications. High precision, intricate and lifetime reactivity mechanism assemblies like primary and secondary shutdown, control and regulation for reactors are also manufactured at NFC. It is the world's only production plant with the capability of producing extremely thin-walled 1.4mm seamless calandria tubes while maintaining a wall thickness variation within 100 microns. NFC's highly qualified think tank and competent technical team consistently invest in the world's best production, testing, and inspection facilities. The Quality Assurance Group carries out several destructive and non-destructive tests along with nanoscale microstructural characterization to ensure the quality of the finished product. NFC is a major contributor to the Make in India dream, where the spark of passion ignites the fuel of innovation. Team NFC has come a long way in indigenizing machinery and devising techniques that enhance productivity. NFC has indigenously developed special purpose equipment to enhance productivity and quality. ISBU for appendage welding in fuel tubes is a state-of-the-art machine that was also exported to the Atomic Energy Department of Turkey. An automatic pellet stacking and loading system was devised to eliminate manual stacking and to reduce human exposure to radioactive material. A final compaction press was designed to produce screened compacts of uranium dioxide. NFC's commitment towards environmental protection shines forth in unique initiatives such as the electrocoagulation unit developed in-house for uranium decontamination of water. At NFC, employee safety, health and progress are accorded to the highest priority. A well-defined occupational radiological monitoring program is operational to estimate the actual exposure of workers and to demonstrate compliance with regulatory limits. NFC leads the way as an eco-friendly organization. All systems are in place to ensure a healthy environment for employees and the general public. Determined to do good by doing good, NFC plays the role of a catalyst in nation building. NFC provides facilities like schools and colleges, 24/7 security, playgrounds, community hall, shopping complex, the health center Sanjeevani, and others for the benefit of its employees and their families. NFC established a dedicated training school in 2001, the BARC Training School, Hyderabad. Caters to the requirement of skilled engineers for the Department of Atomic Energy. NFC's versatile expertise is utilized by several customers cutting across industries. NFC, an epitome of self-reliance in nuclear fuel fabrication. and a major contributor for sustaining the long-term energy requirements of the nation. Also holds the record for 100% customer delight. NFC, fueling the nuclear power program of India, making the India of our dreams, making an India that is safe for our children, making an India our children can be proud of.
भारत माता की
PPT. I think this film was visible to all the people and audible also. I apologize for some technical problem in the beginning. But my idea of showing this film was for many of the people who had been associated with NFC to again recall back their association and with the NFC and various things which are associated with NFC. This one, full slides. So here and also because as I'm hearing that a lot of students are also joining, so it would have been good idea to know them that what NFC is doing and what are the various processes which are done to achieve various products which are produced here. Here I have tried to, no, it's not moving. Okay, remove from there. So my presentation, basically, I want to give a little bit background about energy scenario in our country and how nuclear energy is going to play a role in that and what is the importance. And regarding the introduction of NFC, we have already covered in this film. So I'll not be talking much about various activity. However, I'll give some flavors and some important things. And then how growth of nuclear power in India and how NFC is going to play a role in that. And I'm going to specifically talk about some effort in the automation in the fuel production activity, which has been recently carried out. I'm going to give some detail about that and how it has benefited in terms of quality and the productivity of the fuel. And then summarize my presentation next. So we all know that India is producing nearly 400 gigawatt. They have installed capacity of electricity is nearly 400 gigawatt, and majority of them is produced by coal, that is nearly 57%. And nuclear at the moment is very small, hardly 1.74%, that is 6,780 megawatt is the contribution in the total installed capacity. And we also have a contribution of now large portion by solar 15%, wind 10.5%, hydro 12%, and gas 6.4%. That is the present scenario, and that's from where we have to start next. And if we compare ourselves in terms of other developed countries where the energy consumption is an indication of the socio-economic development, about the literacy, longevity, GDP, and human development. So we stand quite low in that. You can see among the many countries, our consumption is only 972 kilowatt hour, whereas a developed country like US, which is nearly 12 times of what we are consuming.
Dinesh, blow it up, make it big, make it a full screen.
It is a full screen now. You're not seeing full screen?
No, the next slide is not full screen.
Just
It's
see
not
that
full screen.
sharing.
It's not full screen.
Okay. Oh, just a minute. We have to do it.
It's okay. No, it's okay. No, it's okay.
Okay. Okay.
Now it is full screen.
Okay.
Okay. What I was saying that if you have to increase from 970 nearly 1,000 to 1,500 kilowatt level, then by 2030 we have to have a generation capacity of 500 gigawatt, and similarly by 2050 we have to have 700 gigawatt to improve the consumption per capita to the level of 2,500. So there is a need to increase the electricity generation in a big way. And that's where we have to have a basket of energy from different sources to meet this requirement. Next. And if you look at the way we had been producing energy and what was our requirement, till last year, we will say that we had been lagging about our requirement, which was in the peak time almost 10% less than what we required. And 2021 figure is nearly this is showing nearly 940,227. That is the million unit of electricity which we are being produced required. And if we predict that in next 5 years, if we have a GDP of 7.3% or 8% or 6.5%, then by 26-27, how much electricity requirement will be there? If you see the figure from 20 to 21, it is nearly doubled. So in 5 years, by 26-27, we have to double the generation of electricity. That's a huge requirement. And that's where each one sources of electricity has to be harnessed to meet this requirement. Next. And we all know that the main source of energy at the moment, we are using coal, but the coal is generating so much of pollution. And you can see to produce 2000 megawatt, every day we release 42,000 of CO2 and nearly 1,300 tons of ash. So that's a huge pollution of our environment. And if we have to set up a plant of 1,000 megawatt of various types of electricity producing plant, then fossil and nuclear sites are the lowest requirement, 1 to 4 kilometers square. And as you go to solar, it becomes very large, 20 to 50, wind, it becomes 50 to 150. And like that, different sources, renewable sources requires huge amount of land, which is in scarcity in our country. So we have to see that fossil and nuclear both are harnessed in the way that we can meet the requirement with the less land requirement and less being polluting nature also. And if you see the amount of fuel required to produce 1,000 megawatt of electricity, uranium requires only 30 metric ton, that is the nuclear, where the coal, it becomes 2.1 million metric ton. That's a huge quantity of coal which is required to produce 1,000 megawatt, and then of course it's generating huge amount of pollutants also. Similarly, other things also, if we see there's a large requirement of the the various resources which is required for different kinds of electricity generation. Next. And we see that all the gases, greenhouse gases which are being emitted, 40% is coming from the power sector alone. And Indian electricity generation is predominantly 70% is coming from fossil fuel. So which every kilowatt generation produces 1 kg CO2. So we do not have liberty to increase too much from the fossil fuel to meet the energy requirement because of the huge amount of CO2 which is being released. That's why we have to see that nuclear energy becomes more affordable, and that is the only green energy which can be increased to the level which is our requirement, and which will also keep our environment safe. So there's a major requirement that nuclear energy contributions should be increased. Next. And if you see, there are 500 reactors which are operating in the world, highest being in the US, nearly 92 reactors are operational. And like that, many countries have very large number of reactors which are operating. In India, right now, there are 22 reactors which are operating. Next. And you can see that nuclear energy is a major source of energy in many of the countries. France, which is the leading one, which has a 70% contribution. Similarly, Ukraine and other countries, Belgium and all that, they have more than 50% electricity coming from nuclear energy. So these countries have demonstrated that it is possible to make nuclear energy as one of the largest contribution of the energy sources for meeting the requirement. Next. So we have seen that we have to increase the contribution of nuclear energy, and for which the nuclear fuel complex has to play a major role in meeting those requirements. And like in the film, we have demonstrated that major product in the nuclear fuel complex is the fuel fabrication, which we are making for PHWR and BWR. And also all the structured in-core structure material, which are mostly zirconium based, are being manufactured here. In addition to now steam generator tube and other things also being manufactured. So these are the various product mix which are made here to meet the requirement of our nuclear power program. Next. And these are the different types of fuel which are shown in the fuel: 19 element, 37 element, 6x6 BWR bundle. All these are being made here, and which is meeting all the requirement of our nuclear power program. Next. To meet the requirement, we are seeing that in fact what we call here is the ore to core. That means starting from the raw material, from the ore, we are refining the material to achieve the final product. For example, we have two stream, one is the uranium, another is zirconium. So uranium, we are starting from a yellow cake or some UOC, different kind of sources, converting it to the powder, then pellet. Similarly, zircon sand, which are obtained from the coastal beaches, and that is converted into zirconium oxide, then zirconium metal, and then ingot, and then component. And all these are then combined together to get a fuel bundle. And you can see in the left and right side that there's a very large number of processes which are involved, mostly in the nature of mechanical, metallurgical, chemical, and other mechanical in nature. So it is a very intense processes which are involved, a very large number of processes required to finally achieve the fuel. Next. Looking at the present scenario in our country, we are having, as I said, 22 reactors, and we started from a 220 megawatt reactors, then we graduated to 540, and at the moment there are 4 reactors which are in very advanced stage of 700 megawatt of commissioning, and very soon they'll be also available. So at the tentative program is that India wants to achieve nearly 64 gigawatt of electricity generation through nuclear energy, and in which 20 gigawatt will be achieved through PHWR program, and other 45 gigawatt will be coming from a combination of LWR reactors and fast breeder reactor. And this is the program, and we are determined to achieve that. Next. And these are some 16 reactors of 700 megawatt which are coming at different locations, which are already at different stages of erection. And also that Kudam 2 reactors are operating of LWR, 2 are under erection and commissioning, and 2 more is going to come up there in future. So there will be 6 of 1000 megawatt each at Kudam will be there. So all these will be meeting that requirement of 64 gigawatt production from the nuclear energy. Next. To meet the requirement of this PHWR, which is, as I said, that 16 reactors of 700 megawatt is going to come, and they are likely to be commissioned by 2030 or 2032. And after 25-26, nearly every year 1 reactor will be commissioned. So with the commissioning of these reactors, fuel will be required. And if you look at the fuel position right now, production position, the blue line shows that we are producing nearly, our requirement is nearly 1000 megawatt, 1000 metric ton of fuel, and it will continue to increase as we shown by the red one, that how with the commissioning of a new reactors, how it will increase. At the moment, our production is more than what is the requirement, around 800 ton is required, but we are producing on an average 1200 to 1300 metric ton of fuel. This will reach to the highest level of nearly 3000 metric ton. So we have to reach to the level of 3000 metric ton by 2032 to meet the requirement of additional 16 700 megawatt reactor. Next. And not only the fuel which NFC has to produce to meet this requirement, of 2,000 metric ton of additional fuel. We have to also now make structures for 2 to 3 reactors every year. That is quite a big demand. Earlier, we used to make a pressure tube and calendar tube once in 2 to 3 years, or 4 years. Now we have to make 2 to 3 set in 1 year. Similarly, the reactivity mechanism, and also we have got now order for 40 sets of SG tube for the 10 fleet mode reactors. NFC has got an order to produce these 40 sets of SG tubes. All this has to be delivered to meet the requirement of the 700 megawatt PSWRs. Next. How we are going to achieve that? We are having two way of achieving it. One is that augmenting the facility, and the second is introducing the automation, so that the productivity and quality both can improve. And towards capacity augmentation, we already have in very advanced stage of commissioning of NFC quota. I'm going to give some detail at the later stage if I have a time. And automation, I'm going to talk a little bit in this presentation, where it is helping us in improving the productivity and quality. Next. So why do we need automation? We have seen that it was very large number of chemical and metallurgical and mechanical process, very large number of intricate components are handled, and nuclear grade quality requires intense inspection at every stage, and the target is zero failure. In nuclear reactors, we cannot afford to have failure, so we have to achieve zero failure. So therefore, a reliable and reproducible way we have to produce every item. Next. So like I mentioned earlier itself, that these are the various components which goes into making the bundle. Next. And just to give you example, that to make a bundle, one bundle which is weighing around 21.5 kg, this is a 37 element bundle. If I have to make 3,000 metric ton, I have to make 1.4 lakh bundles of fuel. And each bundle has 1,200 numbers of pallets. And if you see for 1.4 lakh bundle, it will become 16.5 crore of pallets, has to be produced every year. And we have to produce 18.5 meter tube or 2,590 kilometer tube. And the special pack, 2.18 crore numbers, bearing pack, 75 lakh. So you can see that huge number of components are required to be manufactured, and then they have to be inspected for their quality. And also fabrication efforts, if you look at that, one bundle has 622 numbers of welds. And if you talk about 1.4 lakh bundles, it has 8.71 crore number of welds. Each one has to work perfectly, because we cannot afford that it may fail. And that's why it requires inspection at every stage and different stages of fabrication, and nearly 100% inspection is done for every component here. So that's why this, we had been doing many of the operations manually, but then reliability part and reproducibility part was questioned sometimes. So we did a lot of effort in improving the automation. Next. So one of the plant, which is a uranium oxide plant, now today we have fully SCADA, PLC based SCADA control plant, where everything is done from the control room, and all the operations parameters, everything is monitored through the control room. And because of this control, we are able to control all the parameters and the quality. Next. And if you look at that, what we have benefited by this is nearly 99% OK lot we are getting, 20% reduction in the process reliability, 40% reduction in the man shifts. In the last 3 years, we have considerably reduced the requirement of resources. And also, one of the major thing in a fuel plant is the reduction in average air reactivity. More than half it has been made by introducing these automations. And also conversion cost has been also reduced. One of the highest recovery worldwide, 99% is the recovery in our uranium oxide plant at the moment in both Block A and Block B. Next. We have also done a lot of automation in our palletization plant, where we convert the powder to the pallet. You can see a series of 6 items which are mentioned. Literally every operation which were manual, we have now converted into automated. So starting from the powder to the green compaction to the finally centering, taking to the centering, and discharging system, grinding system, everything has been automated. I'll be showing a small film on that. And this has resulted again in a big benefit. Next. Quality has increased from 67% average what we are getting in the pallet. Now we are getting 87%, which is equivalent to 1.16 crore pallets not being wasted. Reduced variability in pallet quality, increased productivity by 30%, handling defects has been reduced, and again radiological safety has been improved by 15%. All this has resulted because of introduction of various automation effort. Next. Assembly also has been always was more automated. Now we have introduced more like automated appendage welding, integrated end cap welding, and automated end plate welding machine. All this machine now, which are mostly in-house designed, conceptualized, and fabricated locally, are in place, and every aspect of the assembly is now done through automation. Next. Here, one of the biggest advantages is that 99% is the consistent bundle recovery. Our average rejection of the bundle has come down to nearly less than 1 bundle in a month. And that shows the improvement. And of course, there are other improvements which has been achieved other than that. Next. We have also introduced various handling machines where earlier manual operations were there. For example, movement of the pallets, loading of the pallets, grinding of the pallets, stacking of the pallets. All these were earlier being done manually. Today we are doing in everything through all this automation, and these machines are now working 24 hours with a full reliability. Next. And also we have introduced many inspection systems which is now in line. For example, we are now, after welding the tube, we are doing the end cap welding test, UT test. Earlier we were doing manually, and that to only 5 to 10%. Today we are able to do 100% because this has been now converted into fully automated inline facility to do the integrity test of the end cap welding, which is the major source of error. Next. You have seen that crores of these components are required to be tested, to be measured, and all this today is being now inspected through the automated machines. And I want to share here that we have got a lot of support from RRCAT Indore, who have made various equipment for us. And very short span of last 3 years, we have introduced 35 inspection equipments which were manual and which has been converted into automated inspection units. Next. This is a very important thing we have introduced. We make pressure tube, and this pressure tube, we have now automated the whole UT inspection, and this also is digitally recorded. This is very important because we have to keep this data for whole life of the pressure tube operation, which can go from 20 years to 30 years. So during that time, we have to have all this data for doing any kind of a post-mortem analysis in case of any variation in performance. Next. Inspection now is completely as automated, and this has various kind of not only the dimensional measurements. We have to see the helium leak test. We have to do king test. So many tests are done to qualify the bundle. And all these, you can see the series wise, it is mentioned there. All this is now inspected through automated way. And this has definitely improved in a very large way. The quality of the bundle, as I said, that maximum 1 bundle is getting rejected in a whole month. Next. Just to show example, this is an end plate which is connected to 37 elements to make a bundle. Earlier we used to measure it by screw gauge and vernier calipers, and there are some 15 measurements are to be done for the curvature and different kind of a complex. measurements were being carried out, and half an hour operator used to take to do all the measurements. Today we do by this vision-based testing machine, and we can do in fraction of second. And also we can record all the data, all the dimension for whole life of this mandal. Next. And then we have also introduced various kind of furnaces and other things which has been automated. This all has resulted in improvement in the safety, reliability, and reduction in manpower, reduction in various consumables because of better management. Next. These are the various handling equipment. Next. So overall, by introducing various kind of this automation, one of the major thing that today fuel reliability index has reduced from 0.37 to 0.037, which is one of the best in the world. Today, we are consistently achieving in most of the reactor. This is a huge improvement. The failure rate have drastically reduced of the bundles at the site. And also the rejection of the bundle is negligible in last 3 years at the site before loading it into the reactor. We have improved the quality to better than 85%. Specialties we are achieving better than 90%, and 30 to 40% increase in productivity across all workstation. No reportable incident in the safety in last 2 years at NFC, which used to have 7 to 8 incident in a month. Today is nearly 0 in last 2 years. And JETC is nearly 4 years. In fact, we got a safety award first time after 13 years at NFC. And one of the major reason was introduction of automation at different station. And of course, radiological safety, we have improved considerably. Economy has also improved because of considerable, like one example I'll give, that overtime allowance we have reduced nearly by 80%, and which is nearly saving of 32 crore per annum. Next. And the major thing which we have been appreciated by the ARB and other agencies, that we have improved 60% reduction in average air activity in fuel fabrication plant, which is extremely big improvement, and 40% reduction in total occupational dose. You can see that we have reduced nearly half of the occupational dose by reducing the number of people at the shop floor, and also having a better system there. Our nearly 100% samples are below DAC level, which is permitted by the ARB. So this automation, all that has helped hugely in this effort. I'd like to play a very small film of 2-3 minutes that is about the automation thing. So can you play one film? This one. So this just gives some glimpse of various automated way the fuel fabrication which is being done, and this is a good progress, and we hope to achieve in another 1 or 2 years nearly 100% automation. The way it is being done in international fuel fabrication plants, same way we wish to achieve at our own plant also. And the similar, all these things are being implemented at the Kota Power plant, where Rautbata plant, where our fuel fabrication facility is coming. Next. So one more activity which we all know that we specialize in making the seamless tube. And this seamless tube means it's not a welded tube, and all kind of special material. You name it, whether it's apart from zirconium, we have developed the expertise because of dealing with the zirconium material. But now we are expert in making the tubes of titanium based, nickel based, and zirconium. Of course, we are making stainless steel and various different kinds of requirement of defense, space, and all that is being met to meet the requirement of tubes, which are very, very critical for the requirement of the special applications. I'll show some examples next. So this is basically just shows the various facilities which are required to produce the tube. Basically, we have to produce an ingot. From the ingot, we have to do the extrusion to make a hollow blank, and then we have a series of filtering machines to achieve the different dimension with a different texture and microstructure. And then with the intermediate annealing, we have special furnaces to achieve that. And then we have to straighten them and grind them to get a surface finish as required and the quality as required. So this is just common various steps which are involved in producing seamless tube. Next. So just it shows that, for example, to make a tube of this is this is a titanium based tube, and you can see that it can have nearly 5, 6, or 4 various kind of stages depending upon that what is the dimensions we have to achieve. And these all just shows that what we have made and supplied recently. We have next. Can you remove the title on the top? I'm not able to see the title of the slide. No? Okay. So anyway, this is the titanium tube. We call it titanium 24. It's a very special tube. Now this is 100% make in India effort. We have successfully made it with more than 90% recovery, and the cost has been reduced by 10 times. Whatever it was being procured at that value, today we are making it 1/10 of the cost, and the quality is nearly 93% and above. We are achieving it. Next. That point. Yeah. So pressure tube, of course, we have successfully made it, and recently we have developed a new fabrication route for the pressure tube, especially for the 700 megawatt, and later on we also achieved for 220 megawatt, and we are able to achieve the texture, microstructure, and other property requirement in terms of fracture toughness and all that, which is much better and superior to the other internationally all levels of product. And the performance of these tubes are expected to be much better, and it is expected to have much less creep rate, both in the diametral creep and axial creep. And this we are very successfully making with a very small variation in the properties. Next. And we have now made a state-of-the-art inspection facility. And today everything is in an automated manner. This is inspected, and we are able to supply a very high quality of pressure tube both and calendar tube. Next. In Kona 600 and 690 tubes, which are required by the Nuclear Reprocessing Board, so far they had been importing it, and today we have now supplied them 13 types of tube of various dimensions and various properties. And this is the first time it has been made in the country. and now we have become completely self-reliant, and we don't have to bother about the importing a costly tube and also having other restriction in import. Next. Incodel 800, this is used for our SG tube, as I said in the beginning. Today, we are making nearly going to make 40 set. We have recently supplied 3 set to BHL. This is a very complex 30-meter long tube we have to make, and you can see that it has to bend in a various radius, and very stringent requirement of quality is required, because it has to perform without any failure in the system, as it has to be in a radioactive environment. And we are meeting the quality what was being imported. So here also now 100% now in-house production has started coming, and we have stopped importing these tubes. Next. These are the various stages of fabrication. Next. Incuna 617, this is a very special material which is required for our ultra supercritical thermal reactor, which is going to operate at 650-700 degrees centigrade. And this material is very, very complex to process. And NFC has successfully delivered this in collaboration with Agicar. And today this loop has been made and it is being tested. And this material has been found to be successful. This is another contribution in self-reliance in Make in India. Next. Jikun Navy, of course, we have been making it, but there has been much improvement in terms of quality and in productivity. Next. SS321, also a special tube required for our submarine program, is being manufactured here. Next. We have a success story of a very special tube. It's called Supani 40 tube, which is a very thin wall tube, 0.25 mm wall thickness, and diameter is only 4.5 mm. And these tubes also is a import substitute. And this tube, which it is said that it took nearly 20 years for Russia to develop, whereas in India, in collaboration with BRC and NFC, we could develop it within 1.5 years. And today we are making 5,000 tubes every quarter. And each tube, the cost has been reduced nearly 25 times. I will not say what is the cost, but 25 times the cost has been reduced for every tube. And again, it was an imported tube. And now we are in-house making. And the recovery we have improved from 2 years back from 30 to 35%. Today, we are achieving better than 90%, which is the highest so far achieved in such kind of material. Next. As I mentioned that we are now in a very advanced stage of developing RR grade niobium, which is required by various agencies, including RRCAT, VCC, BRC, and today we have been very successful. We have achieved to the level of 150 to 160 RR value. We have a target of achieving 200, and this 160 also is the best so far produced in India, and it has been produced, and we have also developed various manufacturing techniques in a cold deformation condition, and this has been supplied to BRC and VCC and also to RRCAT for testing and qualifying the material. Next. We have developed again one of the Make in India effort of producing high purity hafnium oxide, which is used by space and also in our reactor. This has been supplied to BRC, which is a final purity 99.25%. The whole process has been developed in-house. Next. We have made this equipment recently. This is a 180 kilowatt plasma melting furnace. This was earlier imported, and the cost of this equipment normally is nearly 15 to 20 crores, and we have made in few crores only, and 100% it is operational. It is in production line. We have also made EV welding, and which is going to be now introduced in our production facility. Next. So what I try to give in this presentation that what is the NFC is trying to achieve, and what are the expertise which is our level, and what are the efforts that are being done to improve basically the quality and the productivity. Of course, we are improving by improving the quality and also by having a better plant. And one of the plant which is coming up is a Kutty plant. It's another 2-3 minutes film just to give you a glimpse of how it has come up and how much progress it has made. Just play that. Play.
Nuclear fuel complex at Kota, Rawat is being set up for meeting the requirements of supply of nuclear fuel bundles for upcoming 700 megawatts with an outlay of rupees 4,256.20 crores.
Project was sanctioned on 11th March 2014. The project site of an area of 250 hectares.
Site grading work started on 15th January 2015. Project site is of rocky terrain, area grading by rock blasting of 5,90,000 cubic meters and 21 km of bituminous carpeting of roads works completed in December 2017. 4 pre-engineered buildings for project office and 12 numbers of watchtowers and 3 entry gates for completed in November 2017. In-site infra works.
Foundation stone laid by Dr. Shekhar Basu on 9th September 2017 for plant and non-plant buildings.
Among total 96 buildings, 73 RCC framed structures and 23 pre-engineered buildings various sizes.
Most of PHWR fuel fabrication facility plant buildings are RCC framed structures.
All Zircaloy fabrication facility buildings are pre-engineered buildings. Concrete consumed is 2,07,270 cubic meter. Reinforcement consumed is 20,350 metric tons. Total built-up area of plant and non-plant buildings is about 1,22,350 square meters. 45 buildings were handed over for erection of equipment. Administrative building was inaugurated by Dr. K. N. Vyas, Secretary, Department of Atomic Energy and Chairman Atomic Energy Commission on 6 October 2020. Zircaloy Fabrication Facility. In Melt Shop. 2 numbers of 2,000 metric tons hydraulic press commissioned. 2 numbers of vacuum arc remelting furnace erection completed.
In extrusion shop. Extrusion press mechanical erection completed. In forge shop.
Forge press delivered at site. 2 numbers of deep hole drilling machines commissioned. In fuel tube shop. 3 numbers of horizontal vacuum annealing furnace commissioned. Mechanical erection of 65 CRTM Pilger mill completed. In sheet and bar. Vertical vacuum annealing furnace erection completed.
PHWR fuel fabrication facility plant buildings is in 2 modules. Module 0 to all civil works completed. In powder package. Erection of all 91 process stands completed. Piping works in solvent extraction and dissolution area in progress.
Installation of sintering furnaces to numbers completed. Pre-commissioning activity for the same is initiated.
And cap welding machines 10 numbers received at site. Installation of 4 end cap welding machines completed.
Completed all 4 major electrical substations and 3 load centers. Main receiving substation was energized. Total 3,595 metric tons of pipe rack has been erected out of 4,400 metric tons. Centralized compressed air system is commissioned. Township Guard House, boundary wall, site grading works completed.
I think let's stop here. Just wanted to give a glimpse about the progress of this plant. You can close the and it's not necessary. So we can claim that nuclear fuel complex is fully ready to meet the increased requirement of nuclear reactor with the expansion program, and quota plant which is coming up is initially for 500 metric ton fuel. It is likely to be increased to 1,000 metric ton in next 3 years after the commissioning, and the commissioning of the 500 metric ton will happen in another 15 months. And after that, we'll be increasing to 1,000 metric ton in another 3 years. In last 3 years at the quota, we have spent more than 1,500 crore rupees worth financial progress we have made, and that despite this COVID, various interventions, we could make a very good progress in that. Similarly, at Palaikal also, we are going to double the capacity in next 2 years. At the moment, we make 250 metric ton of sponge there. We'll be making 500 metric ton of sponge in next 2 years in that facility. So all these efforts are there to meet the requirement of the nuclear power program. And also we are having a very special capability of making seamless tube for all applications of the country. So this is what is all about energy. I just wanted to give a knowledge to all the people that where we are. Thank you very much for listening and giving time.
Thank you, Dr. Srivastava, for giving such a elaborative lecture. Now, forum is open for questions. Anybody want to ask question? They can ask question.
Yeah. I'm Vishwanath, retired scientist from DAE. First, at the outset, I wanted to congratulate our Dinesh Srivastava ji for the elucidated talk about the entire gamut of activities of nuclear fuel complex and catching up the Prime Minister's slogan, self-reliance and make in India at the juncture, at the crucial and a milestone event of the Golden Jubilee of nuclear fuel complex. My question is whether in the near future or in the we will be able to export the our items or material to abroad. Is there any plan? I want to hear from our
Yes. Okay. So as you have seen that we are making all the effort to improve the quality and to demonstrate that the performance is one of the best in the world. So yes, we are ready, and we are also having excess capacity to manufacture and export. And that's what I was trying to demonstrate after having a facility at Rawatpatta and doubling the capacity at Palaikal. It is possible to export. In fact, zirconium sponge is one of the zirconium sponge as well as zirconium alloy component can be immediately started, export. And there are inquiries, people are inquiring, and of course, because of this, these are the material which requires government policies for exporting it. So mutual, some kind of a bilateral agreement has to happen before such kind of export can materialize. So these things are happening, and it is matter of government also to take a decision in this matter.
Thank you, sir.
Okay, anybody else?
Yes.
Next
yes,
question,
Mr.
please.
Ramade.
Hello.
Muted.
He is muted. Mr. Amarendra, you are muted. You can demute first. Yes. Mr. Narayan, you are muted.
Yeah. Babula, you want to ask question?
Yeah, hey Dinesh, very nice to see
Hi,
you
I'm
here.
seeing you after maybe 20 years. Am I seeing you after 20 years? Very nice to see you. So
yeah.
thanks to Kutty for making it possible to see all of you. Yeah.
You want to ask any question, Babula?
And yeah, I mean, it was very nice to see your presentation in the sense that even though we worked in metallurgy for so long, we never knew what is happening overall. And thanks for that part. And I noticed that on the eastern part of India, there is no reactor, even though very powerful metallurgists came from there.
In Kerala too.
Yeah, Kerala people did not want it. And Dinesh, coming to reactors, is there any effort in India for micro reactors? The reason I am asking is that there is very easy production of heat and hydrogen simultaneously. Everybody wants anyway green fuels. So is there any thinking in the US and China, both are doing this in a big way? I mean, huge investments are going because we don't have the grid problems too much.
Yes.
And
Okay. So yes, basically we are familiar a lot with the small modular reactors, which are SMRs. They are becoming very popular, and within the range of 200 to 300 megawatt, and it has advantage. Advantage of factory-based manufacturing can be done, and modular-based it can be done, and you can add on. Yes, work is going on. Only thing is that there are various kind of technologies which people are exploring. Like some people are going by the PWR, some people are even trying molten salt, and some people are trying fast reactor also. So various kind of philosophies are being utilized to make this. India is working on a PWR. There's a 500 megawatt PWR. The design group has been already created, and they are working on the details of the reactor. So the program has started last 2 years, and of course there was already PWR group was there. The same group is now focusing on a small modular reactors, which is in the range of 500 megawatt. This is what work is going on in that field.
Oh, and with regard to the fusion reactors, do you produce anything like tungsten copper alloys, or tungsten to copper joints, or any such activity in your institution, or else who is doing that? Any idea?
So here actually, NFC is a 100% industrial unit, and we do the development wherever there's a user and customer who wants us to develop it. It is not like a BRC where you see the potential of any work and then you try to develop that. Here we get a very clear-cut mandate to develop a certain things, and we are not working in this fusion reactor related anything. We are not working, and these allies. I'm not aware even in BRC also if people are working in a larger scale. Yes, of course, smaller scale people are working.
Okay.
Okay, next question, please. Next.
Go ahead. Thanks. We'll talk.
Yeah.
Okay, Dr. Srivastava. Congratulations for an excellent presentation. It has given the entire ambit of NFC. And NFC has changed a lot in terms of automation since I have seen it. It has done a wonderful work in the terms of automation, which has improved the quality, as you said, productivity, and reduced the rejection material. And more than that, the failure rate in reactors have reduced by 10-fold. That means it has come down 10 times. So what I observe is that if the failure rate in reactors reduces, the reactivity load on the reactors also will reduce, and the environment, the cleanliness in reactor site also will reduce. So that is what, when the production does the first job clearly, it carries a lot of, or rather reduces a lot of load on reactors, and which is a wonderful thing, which probably you didn't have time to tell that, but it is a wonderful work. I congratulate you, Dr. Srivastava.
Thank you, Uni. Thank you. Yeah, I know you were involved with the performance of the fuel in the reactor, being in PID, and you are expert in, that seeing the performance, that PID and performance analysis you did for, I think, whole life you are involved in that thing. So you can appreciate that. I can understand. Thank you, Ash.
Thank you.
Next question, please. Anybody want to ask question?
Have a comment if everybody has finished questions.
Yeah, please do. Hello.
Questions are over?
No, please
No,
go.
actually, Mr. Amrendra is raising his hand for quite some time, but he's not, I know he is muted, he's not,
Yes, muted. Yeah.
Who is that?
so he's not able to ask.
Armendra
Can somebody
Narayan
tell him?
Pandey.
Yeah, please ask question. Pandey. Please ask question. Please ask your question.
You have muted. You haven't unmuted. Click on that mic.
I can unmute for you if you want.
Okay, do that.
Ask to unmute. I can ask you to unmute. I cannot unmute. I can, if you want, I can unmute. Ask all to unmute.
No, I guess he himself has to do that.
Mr. Pandey, you have to unmute yourself. I cannot do it. Yes, still muted. Dr. Parsardi, any question?
Yeah, I have a comment.
Yeah.
I have been witness to the hot arguments between NPC and NFC on fuel leakage and that sort of thing. Very unpleasant discussions. Now, after listening to Dr. Srivastava and watching the documentary, the enormous gain in reducing air activity, that is one thing which appeals to me. Secondly, the improvement in quality because of automation. These are the two things I noticed. And mind you, I have not been in touch with anything which is going on in the sea for so many years. Incidentally, I was secretary of the AERB, and in that context, I have visited NSC several times, and I used to plead with them that NSC should write its story. I don't know if that's been done or not. I am yet to see Dr. Garg's book about uranium. How much NFC is covered, I do not know. I need to see that. Dr. Farid, with whom I have been in touch for a long time during the past 2 years, used to tell me about the NFC and his story. And unless we write it now, generations are all going in their own story. And compared to what it is now and what it was earlier, it will be a remarkable achievement if the story of NFC is also written in some form. Thank you.
So what is the question?
I have no question. I'm sorry.
No
Congratulations, particularly for reducing air
Okay.
activity. Particularly for reducing air activity.
Okay.
Reducing
Now,
the
Doctor.
ladies indoors. I'm looking as a regulator. Yeah. Thank you.
Thank you. Now, Dr. Meena Ravindra, you can ask question.
Yeah, thank you, Dr. Kutty. No, basically being a person from NFC and having been there just 2 years ago, and even for me, it is a great pleasure to see the remarkable improvements. Of course, it is a work of many years, but the maximum achievement in automation and everything has happened after Dr. Srivastava has joined NFC, and he has driven almost in every field. He has driven, I would say, the improvements. And as family members of NFC, we are all feeling very proud of it. I would like to congratulate him on this occasion. Like, of course, we tell him all the time, but this is another occasion publicly we can express our happiness and pride to have been a part of NFC's evolution all these years. And sitting here and looking at our organization, we feel really proud. It's a classic example of Atmanirbhar Bharat, I would say. And, retrofitting anything like automation is not easy at all. And in a running plant, not a single day production has stopped. Even in Corona times, we have been one of the plants which has continuously run and seen to it that the power reactors have been running without stop. So all these has been possible. He was in the driver's seat all the time. And it has been possible because of the strong feeling of nationhood that runs through the blood in NFC. So I'm really grateful and I'm glad I could attend this talk. Thank you very much, everyone. Somebody was asking about the stock of fuel. I think Dr. Srivastav can answer that. It was in the chat session. Somebody was asking about the stock of fuel available. It's the large, huge stock, I know, but I think he's the right person to answer. Thank you.
No, first of all, thank you, Meena. And as he said very rightly, that we have people here in NFC and also capable. And all these ideas were there. And this is during the COVID time, they conceptualized, they designed, they delivered. And it is a contribution of in youngest lot, I would say. All the ideas coming from the youngest lot. And I have been telling everywhere that the kind of human resources we have in Department of Atomic Energy, I don't think any other organization has. The kind of expertise which is available in BRC and the kind of engineering expertise which is available in industrial unit like NFC, I have never seen anywhere. Means we can do anything, whatever is given to us. Is only that we have to have a better project management. This is where we lack, and that's where if we concentrate, definitely the way DAE has been delivering in the earlier stage, I think I see many senior people who have delivered. I tell everybody in first 20 years, 15 years, 20 years of the DAE program, everything came, like NFC came, heavy water came, reactors came, research reactors came, everything came in first 50, 20 years when India had not seen the industrial revolution, when India was not having resources, still the committed people were there and they delivered everything. And we are getting the benefit of that. And that is what is possible to do. We have people, trained people, we have people having knowledge. It is only we have to see that we work in a project mode and deliver in a time-bound manner. This is what we have to improve.
Dr. Suritandan has some question about uranium availability. So you are
yes, uranium availability.
Long-term program, you need uranium. Have you got uranium enough? Yes.
Okay, uranium, you see, we are producing, it has increasing, but very, very marginally it is increasing. And we have now, in fact, potential of, if you see uranium total deposit, it is a huge number, more than 300 metric ton, 3 lakh metric ton deposit has been proven. But the issue is the only thing is the grade of material, and the huge investment is required to collect that, and the cost of the uranium which is produced here will be higher because of the poor grade of uranium which are normally present. But Tumlapalli and that Kadapa region is now today, it is said, at the highest, at the biggest reserve in terms of the total quantity of uranium has been proven. More than 2 lakh tons of uranium is present there, and very, I will say, shallow level, which can be easily mined. So those kind of things are there. We are in good situation, but in the international scenario, you know that uranium is a level of much superior grade, and that's why they become much cheaper to import and then make a fuel at more competitive cost. Today, if you have to sell your nuclear energy power, you have to compete with all other sources. and then only you can sell it. So this balancing has to be done. And we are importing as well as we are having our own sources.
Excuse me, sir. In our annual general body meeting, we had a scientific session where one of our colleagues, retirees, happened to mention that it is very high quality uranium that is being discovered in Kadapa or yeah. So now you are telling it is not of that high quality.
No. You see, what we were getting, it is better than that. Also, is there in certain regions. So it is like a up to 0.1% grade, 1.12% grade is available. So this is definitely better than what we are having right now. But it's not a huge improvement. You see, when people are having in 1%, 2% abroad, and sometime in Canada you can have even up to 8 to 10%. So there is no match with that, and it's a huge amount of processing cost is involved because of this 0.1%, 0.12%. So
thank you very much,
this
sir. It was really great. We could learn quite a bit about NFC also. Thank you very much.
Mr. Vishwanath MNV want to ask question, but he has still remained muted. Vishwanath, he still can you ask question, Vishwanath?
I have already asked the first question itself.
You already asked question. You want to ask one more question?
No.
He can ask me personally here.
You can lower your hand, Vishnu.
Ask one question.
Lower your hand.
Dr. Pandey has unmuted. He can ask now, I guess.
Yes.
Mr. Pandey, you want to ask question?
Yeah.
Please ask. Yeah.
Audible to you people?
I can hear you.
Okay. Thank you very much, Dr. Srivastava-ji, for nice talk. I would like to have one question to you that you are producing, NFC producing more than the required fuel and tubes. So does it will have any impact of aging because your production is higher than the consumption?
Okay, so if you see that fuel, it is a oxide, which is the most stable form of the uranium. So nothing happens once it is converted in uranium oxide.
Pressure tubes and other things? Pressure tubes and all?
Pressure tube and other structure material we are producing as per requirement. I said about the fuel. So these are structural materials we are producing as per the requirement.
Okay.
And that we can produce on demand. So that's not a problem.
Thank you very much.
Srivastava, shall I ask one question? You're telling zirconium 1% ERBM and zirconium 2.5% ERBM. Are they going to still they are being utilized in all our PHWR, or are you planning to
see zirconium 2.5% ERBM? Already we are now made a standard alloy for our pressure tube. Okay. So we are no more producing zirconium pressure tube, and this is now all reactors have zirconium 2.5. No reactor is having now zirconium 2. Okay. As a pressure tube. And zirconium 1, as you know, is mostly used as a cladding material. So in some of the submarine applications, it is being made for that. Of course, that is also being replaced with the superni and other kind of material. And Kudam-Kulam, there is a negotiation going on that for the future Kudam-Kulam reactors, the fuel will be made in-house. And that's where now we are working, and we want to develop it in-house, those PWR material, and they use zirconium 1 as a clad material. In all Russian reactors, clad material is used zirconium 1. So there we'll be using in a very large quantity zirconium 1 clad material for the PWR reactor of BVR. So that's the negotiation is going on, and NFC is ready to produce that.
One more question, Srivastava-ji. Are you planning to use slightly enriched uranium for our PWR? Any idea, like advanced Cantor reactors?
So yes, see,
or a little bit more. plutonium oxide. Very small amount of PO2.
Okay. So what very high in this uranium is planned for ASWR type of reactors where nearly 20% kind of enrichment is, which is the highest in the civil reactors, which can be utilized. So 20% definitely can be used, but manufacturing is not a big issue because we are already making enriched fuel for the BWR from 1 to 4%, 2.5%. Earlier we were processing here, now we are importing the pellet and then we are manufacturing the fuel assembly. So it is possible to do any enrichment, that is not a problem process. Because once it is converted in a pellet, it is like any other uranium oxide pellet.
Okay, Srivastavaji. Anybody want to ask question?
Hey, I will add a comment.
Yeah, Baburaj.
Yeah. Dinesh, even the
Yes.
PhD work was mostly on this 2.5 niobium. Is that right?
Yes.
Yeah,
I was
mean,
a student of Dr. Sigma Banerjee.
Yeah. So
And
this
was
is
a- he's
one
a
person who
PhD bank.
stuck to the work. And we all change
Yes.
topics, but
No, I'll tell you that I've really been lucky to work in the same material for a long time, and I saw the product being made out of it, and the product going to the reactor and seeing the improvement and improving the knowledge. So that way, yes, I was lucky.
Hello.
Yeah.
Yes.
Anybody want to ask question? Otherwise, we will stop it now. Anybody want to ask question? Last question.
See, I will add one comment what you have told about zirconium 1% niobium. It has got some weldability problem generally. That is why the fuel pin fabrication was a little bit problem. You may be knowing.
This was it is said, but all Russian reactors.
Yeah, they are using it.
So what welding problem you are talking about is not for 1 niobium, it is for 2.5 niobium.
2.5, of course, because of 2 phase.
Yeah, so 2.5 niobium has a welding problem. Not the 1% niobium. 1% niobium can be welded.
Okay.
Okay, I think now already 8:45. I think we will stop it now. If you want to ask any question, you can directly communicate with Dr. Srivastava. So I would like to thank Dr. Dinesh Srivastava for giving an excellent presentation. On behalf of our association, I would like to thank him and finding his valuable time and giving an opportunity to give a presentation, especially that there are a lot of students attending this talk. They will be interested to know about India's nuclear power program. Many people want to join nuclear departments. They want to know how to enter the nuclear energy area. So your presentation was excellent. Your slides were so nice. And I am also very delighted to see the activities taking place in NFC. Now I am very proud of being a Department of Technology man, because so many things, so much automation, so many new developments, and the huge complex coming at a quota is so wonderful. And we are really proud of being DAE people. So wonderful, Srivastavaji, and I am very delighted to have you in our forum. And we will come to you again for in case students comes and talk to us. And I would like to thank you on behalf of our association once more for coming and giving us such a. Thank you very much.
Thank you all.
Thank you for giving me the opportunity, Kutty. Thank you.
You must have here in the office now. How far away you are from the office, from the house?
I'm in the office. It is 8 kilometers. It will take nearly 25 minutes.
Okay,
No problem.
okay. Thank you.
Great, sir. Thank you and good night.
Thank you.
Good night.
Thank you and good night, sir.
Okay, thank you.
Thank you. Now, where is Baburaj?
yeah, I'm here.
Night, everyone.
Nice. Unnikishan is there. You saw Unnikishan? Navraj?
Oh. Hey, is this K Unnikrishan?
You K Unnikishan. You're the same. Where is Unnikishan?
Hello.
Unnikishan is there. Unnikishan. Navraj.
Hello.
Hi.
Hi, Bob.
Hey, Unnikrishan, put your camera on.
Okay.
Oh, okay.
Can you see me?
I could not recognize earlier. Okay.
What happened? I changed a lot?
Oh, no, not at all. No, now I feel that.
All our beards have
no change practically.
Okay. Thank you. You also did not change much, Baburaj.
Hey, I will be coming there on November 1st. I'll be reaching Kerala. നമുക്ക് സംസാരിക്കാം ഞാൻ വരുന്നുണ്ട് ഒരു
Okay. I got your number from Gopalakrishnan. Actually, I wanted to call, but because of some reason or other, I could not get in touch with you.
അല്ല ഞാൻ ഇപ്പൊ ഒരു 3 മാസം അവിടെ ഉണ്ട്, നാട്ടിലുണ്ട്.
We'll
meet. We'll meet.
Yeah, sure. Yeah.
Dr. Parsarthi, thanks for coming and attending this talk. I want to talk to you. I'll call you tomorrow. I want to talk to you.
Yeah, sure. Yeah.
Okay, bye.
Thank you all. Thank you all. Good night.
Good night, sir. Good night. Baburaj, we'll meet. We'll meet.
Yeah, sure.
Panikarji, thank you very much. Panikar, thanks. Shankaranarayanan, where are they? Shankaranarayanan is there. And it's in better condition. Okay, then I think it's already 8:45. We're around 2 hours now.
Okay, good day. Thank you.
Okay, then. Baburaj,
Good
keep in touch.
Yeah.
Panikarji,
see you all in
thanks.
November probably. Yeah.
Pandaji, thank you very much.
Yeah.
Thanks for attending. Shankaranarayanan, namaskaram. Parsarthi is there today. Parsarthi is there.
Yeah, it is nice. Very good. Extremely good.
Okay, then we'll finish off. Too tired now. Okay, see you.
Okay.
Bye.
Okay then. See you everybody. Yeah. Bye.